Hello, this is our third video for Chapter 7. This is going to cover sections 6 and 8. Just a reminder that Section 7 was covered in our first video, and we are actually skipping Section 5. This video is going to be all about the E2 reactions. So we're going to start just like we did with the SN2 reaction. We're going to look at the general reaction as well as mechanism. So here is our substrate, and remember we defined this last time as our carbon structure that is connected to our leaving group. This portion is our leaving group. And then within E2 reaction, we're going to react it with base. And our base's job is going to be to remove a hydrogen on one of the beta carbons. So the carbon where our leaving group is attached is our alpha carbon, and then this one actually has 3 different beta carbons, but they're all equivalent, so we can think of it as any of them. And as a result, we're going to create an alkene. Our base is now bonded to that hydrogen that has been removed, so it's now a water molecule. And we have our leaving group over here as well. So here's our new double bond. Our alpha carbon has had its leaving group removed, and our beta carbon over here is now a CH2 instead of a CH3 because its hydrogen was removed. Underneath this, we can see the mechanism for this reaction, so how it's happening. So here's our base. This reaction is going to require 3 electron pushing arrows, and it's a concerted reaction with happening at once, so it's in concert with each other. So here's our first arrow. Our base is forming a bond with our hydrogen. So this is a proton transfer step. Hydrogen can't have more than one bond, so it has to break the bond to the. We're going to take those electrons and put them right here in between 2 carbons. So this arrow is the creation of that double bond. And then our third arrow is going from the bond between the carbon and the leaving group right onto that leaving group. And that's showing us a loss of a leaving group, and in this case it's our bromide that is breaking off and creating that anion. So we do call this an E2 mechanism. The E is for elimination, and the 2 is bimolecular, meaning 2 reagents are involved at once, the substrate and the base. Just like with our SN2, our transition state is bimolecular. So that's what they have in common, is they both have the 2 in their name, they both involve 2 things in their mechanism, as well as their rate law and their transition state. We're going to talk about the regioselectivity in a few slides here. E2 reactions have a couple other names. They are also called dehydrohalogenation. The D tells us that we're removing something. The hydro means hydrogen, and halogenation, or halo, is our halogen. So this is saying that in the reaction, we're removing a hydrogen and a halogen. It's also called a beta elimination because in addition to our leaving group, we are eliminating a hydrogen from that beta carbon. And it's also called a 1-2 elimination because the 2 things that are being removed, the leaving group and the hydrogen, are on adjacent carbons, 1 and 2. And remember, when we number something in this fashion, we're using it to signify how close they are to one another. It has nothing to do with the numbering we would use for naming it. So this is our general reaction and mechanism for this reaction, for our E2 reaction. So we do also need to talk about the rate law. And just like with any reaction, it's based off of our rate determining step, our RDS, and because it is bimolecular, both of our reagents are going to be included in that rate law. So our rate is equal to K, our rate constant, times the concentration of our alkyl halide, our substrate, times the concentration of our base. So it's first order with respect to our substrate, and it's first order with respect to our base, which makes it second order overall. And we can that this is true because it is also a bimolecular reaction. So step, which is also our rate determining step. And just like with the SN2 video, the last slide for this is really going to be a summary of all of the important information for the E2 reactions. So we talked about the substrate with SN2. We're going to talk about the substrate here with E2 as well, but what we're going to look at when we react a SN2, when we react a substrate and it goes down an SN2 pathway, we had to look at how sterically hindered it was. And we saw that if something had less substituents, faster in an SN2 reaction. I've also talked about that a lot of reagents can act as a nucleophile and as a base. So the example that's being used here is hydroxide, and it can do both functions. When this situation occurs, that means that our SN2 and E2 pathways competition with each other. So the example that's being shown here is when we try and use our hydroxide as a nucleophile going down that SN2 pathway, it gets blocked. There's too many substituents in the way. But when we use our hydroxide as a base and we go down our E2 pathway, we can easily access a beta hydrogen because that's not the portion that's sterically hindered. So when we go down these pathways, is that a sterically hindered substrate will favor that E2 reaction if we have to choose between SN2 and E2. That competition is something that we'll talk about more in a later section of the chapter as well. We have a whole section that talks about the competition within these reactions. Now, one of the big things that we do need to discuss with two reactions is regioselectivity and stereoselectivity. Regioselectivity is when more than one product is formed, but one of them is a major product. So here's our example. We have 2-bromobutane, and in our E2 reaction, we're going to lose our leaving group, but we're also going to remove a beta hydrogen. Now, there's 2 different beta carbons here with hydrogens attached to them, and if we remove a beta hydrogen from this carbon, we will make this product. So let me highlight this in a different color here. So if we take away this hydrogen, we will make this product. And if we take away a hydrogen from the carbon on the end here, we will make this product. So there's 2 different possible products that can form. 2-butene, which also is telling us that there's a mixture of E and Z isomers, so we'll get to the stereochemistry part in the next couple slides, and 1-butene. Now the percentages underneath these are telling us what percentage of the product is from each of these products. So 80% of the product is 2-butene and only 20% is 1-butene. And with that information, we can label these and say that 2-butene is our major product. So that just means that it's the one that's in a greater quantity. And 1-butene is our minor product, or the one that's in a smaller quantity. Now here's our rule of thumb. The major product is the one that has a more substituted alkene, and we call this the Zaitsev product. There's unfortunately exceptions to this rule, and we'll get to those on the next slide, but this is a good rule to follow as long as we know what the exceptions are. Now, in order to follow Zaitsev's rule, we want to remove a hydrogen from the beta carbon with the fewest hydrogens. So if we look back at our starting material here, the beta hydrogen on the right has 2 hydrogens, or excuse me, the beta carbon on the right has 2 hydrogens, and the beta carbon on the left has 3 hydrogens. So if we remove one of those 2 hydrogens, we're going to our Zaitsev product, which is our major product. And when we say it's a more substituted alkene, if we look at our alkene, it has 2 carbon substituents coming off of it. And if we look at our alkene over here, there's only 1 carbon substituent coming off of it. And this was something that was also covered in the first video. The minor product then is going to be the less substituted alkene, and we call this the Hofmann product. So let's look at a couple of the exceptions to this, and then we're going to do a couple practice problems. Now, the Zaitsev and the Hofmann product being major and minor is based off of steric hindrance. So if we are using a base that is more sterically hindered, then it's going to be more difficult to get to the more substituted side, the more substituted beta carbon. So if we're using a more suited base, then the major product will be the Hofmann product, or another way to say that is that the major product will be the less substituted alkene. So here's our exception right down here at the bottom. The Hofmann product will be the major product if we're using a bulky base. So let's define bulky base and look at the data on here. So in this first example, we're using ethoxide. And ethoxide is an ethyl with a negatively charged oxygen. And our products are 71% Zaitsev and 29% Hofmann. So the Zaitsev is our major product, the more substituted. As we bump up in size, so now we're using a tert-butyl group. So this is also referred to as a tert-butoxide. The percentages completely switch, and now our Hofmann is our major product. And then we go up to this last one on our chart here, where we have an even larger group attached. We have these 3 ethyl groups attached to that carbon in the center, and our Hofmann is 92% of our major product. We have 3 very common bulky bases up here at the top. We have our tert-butoxide, and in this first example, it is paired up with a potassium as a counter ion. So you'll see it written like this, TBU-OK. So tert-butyl, the TBU, O for the oxygen, K for the potassium. You'll also just see it written with a TBU and then an O with a negative sign. The next one is diisopropylamine. So 2 isopropyl groups attached to an amine. This one is labeled as DIPA. So these are good abbreviations to learn, as well as to create a list. And then our last one here is triethylamine, and we abbreviate this as T, so TEA. I mentioned to keep a list. I'm going to put some information up on Canvas on starting an organic reactions notebook. It's a good way to learn about the reactions as well as create a reference for yourself. So it will be useful next semester. It will be useful as you move on to higher classes, as you're studying for the MCAT. And one thing I suggest doing within that notebook on the back couple pages is to make a list of all of these abbreviations, because we're going to end up with quite a few of them, and so it just becomes a nice reference for yourself. I'll put some information up possibly during spring break, but I'll create something for you guys so that you have those references and something to keep you busy. All right, so we've looked at the Hofmann. So we're going to do a couple practice problems with this. We're going to start with this structure. So we have a pentane that has a methyl substituent and an iodine substituent, and we are going to react it with two different bases. So a tert butoxide and a sodium hydroxide. So really, this means we're reacting it with a small base, and we're reacting it with a large base. And we want to write down the major product as a result of each of these reactions. So we're looking at our structure here. That's our alpha carbon. So we know that our iodine is going to leave from that carbon. And we want to remove a hydrogen from a beta carbon. So we have three to choose from. There's a beta carbon there, a beta carbon there, and a beta carbon there. Now the two that are on this side are both methyls, so they're really equivalent to each other. So I'm just going to erase this one because they would be equal to each other. It doesn't matter which one we'd pick. So really, we have a beta on the left over here, which is a CH3, and we have a beta carbon on the right, which is a CH3. Oh, excuse me, a CH2. Because on this side, we're using a small base, our major product is going to be our Zaitsev product. And our Zaitsev product tells us that we should remove a hydrogen from with less hydrogens. So my product will look like this. I removed a hydrogen from this carbon, I removed my leaving group, and now I have a new double bond between the alpha and the beta hydrogens. On the other side, we're using a bulky base, and so my major product is going to be my Hofmann product. And so that means I want to remove a hydrogen from the side that is less sterically hindered, or another way to think of that is we're going to remove a hydrogen from the side with more hydrogens. So I've taken off my leaving group, I've removed a hydrogen from that beta carbon, and I end up with a new double bond between the alpha and the beta carbons. So we can create from this reagent by changing what type of base we use. Okay, we're going to do a couple more with this. In the next problem, we're going to specifically use a ring. So we're starting with our ring attached. There's two methyls to the right, or excuse me, to the left of it, and we're reacting it with sodium ethoxide. So just as a reminder, when we see that sodium, we can ignore it, and really this is an ethoxide ion. We know that is our alpha carbon. That is our leaving group. When we look at the beta carbons, there is a beta carbon right there, and there is a beta carbon right there. But we can't in our reaction because it doesn't have any hydrogens attached to it. So we're going to remove a hydrogen from the beta carbon to the right, and I'm going to draw out the mechanism for this one, just so we have a little bit of practice with that. Oh, sorry, I dropped my microphone. Let's prop that back up. Okay, there we go. I'm sure that was very loud. I'm sorry. All right, I'm going to have three arrows, remember. We're going to go from our base to our hydrogen. We're going to go from the bond between the beta carbon and the hydrogen to right there. That's what's creating our double bond. And then I'm going to go from the bond up onto that leaving group. So we are doing our proton transfer and our loss of our leaving group. The little arrow is really just to show our flow of electrons. So the product we get from this looks like that. So we have a new double between the alpha and the beta carbons, and our two methyl groups on the side there unaffected by the reaction. All right, we're going to do one more, and then this will actually lead us into our next topic. So we have a 3-bromo 2-methyl pentane. We're going to react it with hydroxide, and we want to see all of the products. And sometimes it's up to you to draw just the major. Sometimes you're asked for all the products and then circle the major or label them. In this case, we're going to look at all the products. Actually, we'll label majors and minors. So again, we have our alpha carbon. So we have a beta here, and we have a beta over here. So we can start by those two options as our products. And what I mean by that is we can draw a double bond going to that beta carbon, or we can draw a double bond going to that. When we say we want to see all the products, that also is referring to stereochemistry. So this one is drawn as trans, but I could have also drawn it as a cis double bond. So that's something that we're going to have to consider as we move into our next section. Now within these, we do know that because a small base, this one will be our major. Now between that cis and the trans, which one will be next in line? That's where our next slide is going to take us. So we're going to move into the stereochemical side of our reaction, and there's if we have more than one beta hydrogen to choose from, then our reaction will be stereoselective. And so stereoselective means that more than one stereoisomer can form, and one of them will be the major. So in the example up here, our bromine is going to leave, our beta hydrogen is going, and as a result, we can either form the trans product or the cis product. The trans will be made. The trans is going to be the major one because a trans double bond is more stable than, and a lot of that has to do with steric hindrance. So this is a stability issue, and I do talk about this in our first video. Now there's not always more than one hydrogen to choose from. And when I'm saying more than one, I'm talking about the two hydrogens that are attached to that same carbon right there. So if we only have one to use, then our reaction actually becomes steric. And that means that the stereochemistry of our product depends on the stereochemistry that the substrate had to begin with. And the reason for this is because when we remove the hydrogen and the leaving group, they have to be anti-coplanar or anti-periplanar. So those two words almost mean the same thing. Anti-coplanar means that they're going to be completely opposite from one another, and anti-periplanar means that they are nearly opposite from one another. So anti-coplanar means they have to be 180 degrees away, and anti-periplanar means they have to be 178 degrees away from each other. So the two words get used interchangeably quite a bit. So I just want to make sure that you're aware how similar they are. So in the example that's down here, we have our substrate. It's drawn out a little bit different just so we can see that stereochemistry, but we have our leaving group, we have our alpha carbon, our beta carbon, and our beta hydrogen. And here's our base. Our base is removing our hydrogen, we're creating that double bond, and our leaving group's leaving. Our hydrogen and our leaving group are pointed completely away from each other in that anti-periplanar fashion. There's only one hydrogen on this carbon. So the way that it's arranged is the only way that we can create our double bond. And if we look at how these substituents are in relation to each other, we have a methyl dashed line. That tells us that when our double bond forms, they will be on the same side of that double bond. And we have this C6H5, which is an abbreviation for a benzene ring, and a hydrogen that are both on wedges. So again, they will be on the same side of our double bond. So let's look at one more slide with some pictures, and then we're going to do a couple practice ones with this. So this is a different structure. It has some similar substituents attached to it, but we have a beta hydrogen right here attached to our beta carbon. We have our leaving group attached to our alpha carbon. And we have our little eyeball here because we're looking at it with a Newman projection. Now this definitely isn't a required step to do, but it can help to see the arrangement. So as that beta hydrogen is removed, it is anti-coplanar from our leaving group, from our bromine. So hydrogen is eliminated, bromine is our leaving, and our hydrogen and our pH, our phenyl or our benzene, are both on the dashed lines. So they are on the same side of our Newman projection here. So as our structure got flipped around, our dashes are on the left side, and then we have a benzene and a methyl that are on a wedge on the right hand side here. So as we remove those two groups, we're kind of almost just flattening this down. I picture taking my hand on the top and hand on the bottom and squishing it flat, and these two substituents will be on the same side of that double bond, and these two substituents will be on the same side of that double bond. So we're going to do a couple practice ones with this. Really, we're going to do a couple that are easy, and then one that's a little bit tricky, and then we'll end with our summary slide. So to go back to our major product, the one that's more substituted, and then out of our trans and our cis, they both minor products because they're in smaller quantities, but we would have more. So trans will be greater than cis. So sometimes we want to be able to rank them to say most to least. So these are actually in order from most to least. All right, let me erase our little board here, and then I'm going to give us another example to work with where we're going to have to use our anti-periplanar new information. So we have this substrate that has a bromine leaving group attached to it. We're reacting it with our hydroxide, so a small base. So we know this is our leaving group, which means that's our alpha carbon. We have a beta carbon here and a beta carbon here. The beta carbon on the left doesn't have any hydrogen, so I'm even going to erase it. We don't even need to concern ourselves with it. The beta carbon on has one beta hydrogen. Now it's located on a dashed line. Our leaving group is located on a wedged line. So they are already opposites from each other, which means we do not have to do anything to the chain. We can leave it as is. So there's all of my pieces, and there's my double. This is the only product that is going to form. Now if we want, we can put this hydrogen up here. This is the hydrogen that's attached to the alpha carbon. My methyl went from being a wedge to being a straight line because that beta carbon is now trigonal planar, so everything is flat, so we don't use on flat carbons. We're going to do one more that's on the easier side, meaning we don't have to do a whole lot of changes. And we're going to do one in a ring. Rings are often used for these examples because they have less rotation. It makes it a little bit easier to show examples and to show how we utilize this information. So here's our leaving group. We have a chlorine, and again we have the two beta carbons, one on each side, and our beta hydrogens, we do have one on each side there. But here's the difference between them. We have a beta hydrogen on a dash and a beta hydrogen on a wedge. Our chlorine is on a wedge, which means that we can't use this hydrogen because it is syn-planar, meaning they're pointing in the same direction. The hydrogen over here is pointing in the opposite direction. It's anti-planar. So we're going to use that hydrogen, which means we're going to remove that hydrogen. We're going to remove the chlorine. That's the part of the molecule that doesn't change. I still have my ethyl up here, and here's my new double bond. So going between the alpha carbon and that beta carbon. And again, my ethyl changes to a straight line because we have that, we went to a trigonal planar shape. All right, one more, and this one's going to be the tricky one. Oh, sorry. Now this looks a lot like the first one, but there's one important difference. On the first one, we had a methyl right here on a wedge. Now our methyl's on a dash. So same information. Leaving group. We know that our beta hydrogen on the left, beta carbon on the left doesn't have any beta hydrogens. Our beta carbon over here now has one hydrogen on a wedged position. So in the conformation it's in, we cannot remove that hydrogen because our hydrogen and our bromine are pointed in the same direction. So we need to rotate that hydrogen, and I'm going to rotate around that bond right there. So this is going to be after my rotation. So there's my pieces. I'm just going to fill them in. So if my hydrogen is rotating to the dash, then that means my dash is rotating up to this straight line. And my straight line is rotating down to the, this is an ethyl group. And so this is what we end up with. So to get to our final product, we know that we're going to use our base to grab that hydrogen. Those hydrogen electrons are going to form our double bond, and our leaving group is going to leave. So what we end up with is a double bond right here between that alpha and the beta. There's my methyl, there's my ethyl. This is the hydrogen that was attached to that alpha carbon, but we end up with this as our final structure and our only structure. So this is falling into that stereospecific category because there's only one stereoisomer that could form. All right, here's our last slide. It's good because this video ended up being a little bit too long. We have our mechanism in our summary here. The base is removing that beta hydrogen. We're forming our double bond as our leaving group is leaving, and we're creating an alkene. Here's our base with its hydrogen attached. Here's our leaving group. Our rate of reaction is bimolecular, so it's dependent on the concentration of the substrate and the base. For regioselectivity, if we're using a small base, the major product will be the more substituted alkene, which we call the Zaitsev product. The minor product will be the less substituted alkene, which we call the Hahn product. But we can flip the major and the minor by using a bulky base. For our stereochemistry, if there's more than one beta hydrogen, the reaction is stereoselective, which means that the cis and the trans will form, but the trans will be the major product. And if there's only one beta hydrogen, then our reaction is stereospecific, which means that the hydrogen and the leaving group have to be anti-periplanar. And then the last piece of information, which was shown in all of our examples, but I don't believe it was ever stated, is that our base does need to be a strong base. So this generally, again, means a negative charge, and we saw this in the very first slide. There was a table of acids and bases. All right, that is it for part 3 of our Chapter 7 series.